So it's my pleasure to welcome you here to the symposium today, and I'm excited for the panel discussion that we have lined up. So in addition to Mark, I'm happy to introduce our other panelists on the stage with me today. We have Laia Andreu-Hales, who's an assistant research professor at Columbia University. Sitting next to her, we have Tom Knudsen, who comes to us from down Route 1 at GFDL, where he's a research scientist. And then our own Laura Schneider, associate professor in the geography department. And Laura's actually going to pull double duty today because she's going to moderate the afternoon panel, so you'll see her up here again. So each of the three panelists who aren't Mark are going to come up here and talk to us for about 15 minutes about their research. And after those 45 minutes of talks, we're going to open it up for a bit of discussion before Jim comes up and talks to us again about the details of lunch. So without further ado, to try to get back on track, I'm going to invite Laia to come up and give us her talk. Thanks.
Good morning, everyone. Today I'm gonna talk about how paleo perspective can help to assess climate change in the tropics. So paleoclimatology is the study of climate prior to the widespread availability of instrumental records, such as temperature or precipitation, that they usually last as maximum the last 150 years. And why is it important to know about past climate? So the reason is that we need to have a longer perspective to understand the changes of climate in variability and the recent climate change. If we take a look at the distribution of the temperature stations across the world, what we can see is that it's an even distribution. We don't find stations everywhere. And also take a look at the colors below. It indicates the length of the stations, the length of the records of the stations. And you can see that, for instance, for North America and Europe, we have pretty much all covered, and the length of the records is longer, about between 100 and 115 years, but there are some regions of the planet that are completely empty of instrumental records. The colors are a little bit lighter, yellow or even blue. That means that we have records of less than 50 years. How do we estimate past climate variability? We do that using paleoproxies. And what is a paleoproxy? So it's a biological or geological archive that responds directly or indirectly to climate, and it can be used for estimating past climate conditions when instrumental records were not available. So as you can see, there is plenty of variety of paleoproxies, and depending on which paleoproxy we use, we can extend the climate information from centuries or from millions of years. But how back we want to go back in time? So this is a diagram of the geological scales, and we can see that theoretically we can study the entire history of climate of the Earth, but maybe we are not so much interested in that for that talk. We are looking for continuous records of high resolution covering mainly the few thousand years, and which is the advantage of working for this relatively short period or regarding the timescales of the Earth, is that we found very well dated records like these ones. So it's important to take into account that not all the records can cover the same time period, and not all of them have the same resolution. So for the last few thousand years, the high resolution records are like tree rings, or coral, or even lake sediments or some ocean sediments, but it's not so typical. But when we look all over the world, which paleoclimatic data is available, we see that it's very unequal distributed as well. This is data from the NOAA webpage, so all this data is available and free to the public. If we take a closer look to the tropics, and just for the high-resolution paleoproxies like coral, historical, or ice cores, paleotherms, and tree rings, what it's pretty obvious is that in the tropical areas, indicated by the black lines, there is almost there are not many proxies. So now I'm gonna talk about some examples of how paleoproxies, high-resolution proxies, can provide information about past climate variability in the tropics. The first examples is from an ice core record that have like annual resolution in Peru. And what we can see is that measuring the delta O18 on the ice layers, we can see in this picture, we can see that these records have annual resolution. So measuring the delta O18 composition in each one of these layers, we are able to get a record of delta O18 fluctuations that correlates very high with sea surface temperature in the tropical Pacific zone. So then, using this information in the middle plot, we can see how these delta O18 fluctuations correlate very well with SSTs for the El Nino region. And back in the plot below, in the below plot, we can see that thanks to that, we can reconstruct El Nino for the last 800, since 200. Another source of variability of SST and El Nino can be the coral record. Here I'm using an example of corals from the tropical Pacific as well, from Palmyra and other islands surrounded. And what we can see in this picture is a living coral that can last like 200 years old, but we can find in the sea corals that are dead, and we can extend back this register back in time. So for the calibration period, in the plot on the right, you can see that measuring the delta O18 for these annual bands of the coral record, you find also a very good correlations with SST temperatures. Why is this important, or why this can be useful? So this can give us like a longer perspective of ENSO variability. In the plot below, in the plot above, we can see this delta O18 record based on corals, and we can see the oscillations of the delta O18 fluctuations, and just below them, we can see the number of El Nino and La Nina events. And this is just for the last 1,000 years. But if we take a closer look for the 20th century, highlighted in yellow, we can see that these oscillations are like higher. So are at least the same magnitude that the Nino in 1997. These researchers have worked more and more in the area and have been able to extend back the record 7,000 years, and it's what we are seeing in the plot below. In the plot below, we are not seeing the complete series, we are seeing the standard deviation, the variability of different fossil coral records along this 7,000, and also at the right here, we can see the variability of ENSO based on coral records for the 20th century. So what we can gain from that work is that the 20th century variability, it's higher than, It's higher than in most of the fossil record, but it's not unprecedented. So we have this 7th century period here. Anyway, so we have some periods that have had this high variability. This is another thing that we can gain from paleoproxies. This example is how we can estimate the movement or the position of the Intertropical Convergence Zone, ITCZ, based on marine sediments. These marine sediments is quite typical, I would say, because they can provide annual and sub-annual resolution, while most of the marine sediments are just able to record longer time scales. So we are just going to look one parameter, that it's the titanium, the 10% of titanium that we found in this sediment core. We can see that this sediment core covers up to 14,000 years old. And we can see, highlighted in yellow, the fluctuations of titanium. This 10% of titanium will be expressing how much sediment is arriving from the watershed surrounded. And so it's connected with precipitation. More precipitation, more titanium. And this will indicate, in this area, you can see the plot on the left, the Carioco Basin, it's just in the limit of the migration of the ITCZ and receive more precipitation when it's moved north. So looking at the variations of titanium, we can see the position of the ITCZ. These authors go like a little bit closer and were able to link this drought with the Maya classical collapse in 1800. And coming back to tree rings, that it's indeed my expertise, we can see that tree rings are also almost, or there are very few tree ring records in the tropics, and I will explain why. These are the cases that it works, there are some of them. So we have like 1,000 years of tree ring records in Mesoamerica, and they indicate drought variability. We also found this classic Maya period drought in this drought index reconstruction. And other tree ring records in Guatemala also covering 300 years. And further back, about 17 degrees south, we found Polylepis tarapacana chronologies that were able to reconstruct precipitation variability for South America and link to SSTs. Why is the reason? Because there are so few chronologies in the inner tropics. First reason is that sometimes there is a lack of well-defined rings. And this is because in the tropics, we don't have a clear seasonality due to temperatures in winter that stop tree growth. So we don't have this clear seasonality depending on temperatures. But we can have other kind of seasonality more depending on hydrologic or in changes of hydrological, in changes in the hydrological cycle. So here we can see an example in the tropics, in the inner tropics that work. We have like annual tree rings, even if some difficulties with absent rings and false rings. And when we make the radiocarbon curve before and after the peak, we find that indeed there were annual. But some other chronologies that present visible tree rings, when we make the radiocarbon analysis in 3 different trees, we find that indeed they were not annual. Coming back to Asia, I want to talk about this region because the tree ring lab where I work, my colleagues have been a lot of progress there. This is a record from Phocaenia, a conifer in Vietnam that successfully reconstruct drought variability and my colleagues were able to link this myth of Angkor civilization with periods of drought, and this was also validated by other proxies of speleotherms in China, indicating the blue dot, and are like the red and the green ones. Another relevant achievement of people from my lab, from Rosanda Rigo, it's being able to construct a Teak stream flow reconstruction based on Teak from Java, that this is about 5 degrees south. So, and this reconstruction show good correlations with SSC temperatures in the same way that corals from the region show. And why is this important? Because thanks to this effort on building chronologies in the tropics, Ed Cook was able to construct the Monsoon Asia Drought Atlas that gives special reconstructions of climate variability for the last 700 years in Asia, but also including the tropical region in Asia. So we can see here some example of what you can do with this atlas. You have like a network of chronologies, green dots, and then you reconstruct PDSI, that it's a drought index, that it's a gridded product. So you can see in the plot in the middle for different periods, you can study the spatial variability of these droughts. And also you can select some regions and make a mean chronology and study the variability of this region for the last 700 years. As I said, the Monsoon Asia Drought Atlas is a big achievement, but it's only based in 300 chronologies and very few chronologies from the tropics. So this work can really be extended. And this MADA came after the NADA, the North America Drought Atlas, that, for giving you an idea, have like more than 1,800 chronologies and cover 1,200 centuries. And so what is next in the tropics regarding tree rings? So more data it's needed for being able to reconstruct similar drought atlas for South America, for instance, and for Africa. Take home message, paleo perspective, it's needed to be able to fully understand the true range of climate variability. There are high resolutions in the tropics, but tree ring studies are challenging for the reasons that I explained. And for understanding better ENSO, the monsoon systems, or the ITCC immigration, more paleo data is necessary. Thank you.
Thank you, Laia. And keep in mind here that many of us who go to AGU in a few weeks, these talks are even longer than what were allotted at AGU. So good job for getting it in there. So next I'd like to invite Tom to come up and give us his thoughts.
Okay, thank you, Ben. I appreciate the invitation to come speak today about assessing climate change in the tropics. So I just have 15 minutes to cover this, which is a tall order because this is a very complicated issue. So I just want to try to hit some of the high points coming out of our research at GFDL on this general topic area of assessing climate change in the tropics. Here we see a picture of the Typhoon Haiyan, which occurred in 2013 and caused devastation in the Philippines. But the question is whether these type of extreme events might be changing due to anthropogenic climate change. So I'm going to start out with my main points, what I'm going to try to get across in this talk. I have four main points that I want to make. The first is that anthropogenic climate change is affecting tropical climate. We see it in detection attribution studies. It's especially evident when we look at surface temperature trends. And I'll show some examples for surface temperature, including some recent examples of extreme events in annual mean surface temperature occurring in the tropics. The second point, when we then move from surface temperature type of variables to tropical cyclones, then the case is not so clear on whether anthropogenic influence is having an effect. And I'll show some examples using the past data looking at tropical cyclones. We do have, though, projections from climate models of how we think that tropical cyclone activity may change in the future as the climate continues to warm, and I'll show some examples of that from our work. And then the third point I want to get to is El Nino and climate change. Again, what I'll be concluding there is that it's difficult to see an anthropogenic effect on ENSO due to these large internal fluctuations that one sees in long records of ENSO, and I'll show that as well. Then for the fourth point, I want to get to this issue of heat stress changes in the tropics, because heat stress is largely controlled by these temperature changes. And I'll show some examples that I think are giving rather sobering look at what climate change could mean in terms of tropical temperature changes in the tropics, and also the expansion of tropical-like conditions into higher latitudes. So in some sense, maybe the tropics may be coming to us. So we'll see that. Okay, so first, detection attribution of changes. Why do we think climate change is actually happening here in the tropics? So this map on the left is showing 2013 surface temperature anomalies, annual mean surface temperature anomalies around the globe. And you see it's generally warm anomalies everywhere. But what we've done in this figure on the right is to just look where 2013's annual anomalies were the largest, highest ranked first, second, or third in a record of at least 100 years. That's in these red and orange areas. So you see that during 2013, the most unusual temperatures were occurring here over Australia, which I won't talk about today because that's just outside the tropics. But let's look in the tropics here at this region of the Western Pacific and Indonesia region here, where there were extreme annual mean temperatures occurring during 2013. So now, this map is showing this occurrence of these extreme warm annual mean temperature anomalies in 2013. This is a time series of the fraction of the globe covered by, in red is extreme warm temperature annual mean anomalies, the fraction of the globe covered by them, and in blue is the fraction of the globe covered by extreme cold temperature anomalies, and this is from the late 1800s to the present. And you see what's going on here is that in the past few decades we've gone to and this is using the entire record when we're talking about when you have extreme annual mean temperature anomalies, we've gone to a condition where we're now only seeing annual mean positive warm anomalies around the globe. We're no longer actually seeing any annual mean extreme bottom three cold anomalies as we did back in the earlier time. So we've sort of entered this new era here of extreme annual mean warmth. Looking at the time series here for that looking at the time series for this Western Pacific region here in black, this is the observed time series in black, and it's showing this long-term warming in this region near Indonesia. And the red curve is a climate model historical simulation of temperature in the same region, and we see that those track rather closely. The blue curve is climate model simulation, but not including anthropogenic forcing. So this is only including natural forcing, such as the volcanic eruptions I have labeled here. And we see how this observations and this all forcing simulation that includes the anthropogenic forcing is kind of lifting up and separating from from where it used to be back in the earlier part of the record. So this is this emergence of this strong warming that we see there in the Indonesia region. So we can look at this from a detection attribution. This is a sort of a complicated diagram, but this is what we use for detection attribution in some sense. These are the values of trends in these time series using different start dates, and the black curve is the value of trends for all different start dates, but ending at in 2013, and these are generally positive. Now this purple envelope here is an envelope of trends from the climate models showing some uncertainty because we have different climate models, and also uncertainty from natural variability. So it kind of, this envelope expands here for these short-term trends because we have a large influence of internal variability. This green shaded region here is just the types of trends that one can get from just internal climate variability. And what we see is that the observed trends are outside of this green envelope, meaning that we're detecting a climate change because these observed trends are very different from internal variability trends. And they're consistent with the all-forcing trend because they're within this pink envelope here. So that's what we mean by detection, outside the green envelope, and attribution, where we're consistent with this alternative pink envelope. Think of these as two different hypotheses about the climate system, this pink envelope being the all-forcing hypothesis, including anthropogenic effects, and the green envelope being just the unforced hypothesis with no anthropogenic forcing effects. So observations are much more consistent with that pink envelope, which has the anthropogenic forcings. Another way of looking at it is we can take this recent event here, the circled 2013 annual mean anomalies in the Indonesia region, and this is a distribution of annual mean temperature anomalies that one gets from climate models just with natural forcing, so not including an anthropogenic warming effect. And here the shifted distribution is when you include anthropogenic forcing. So this distribution of the PDF of temperatures from models in this region is shifted over to the right. Now here's 2013 and 1998 as individual years, and you see that these individual years lie outside of this natural forcing distribution, but they're just inside the distribution which includes anthropogenic forcing. That means that the risk of this type of event is almost entirely attributable to anthropogenic forcing because you actually cannot get, according to the models, you cannot get an event this large just in the pre-industrial type of climate. Now this conclusion is dependent on these models, but basically this is saying that it's a smoking gun of sorts, that this type of warm anomaly is just not going to occur back in the kind of the pre-industrial natural world. You can do the same kind of exercise that I described and see where temperature trends are consistent with these all-forcing climate model runs that include anthropogenic forcing, and where they're inconsistent with these models that don't include anthropogenic forcing. That's in the red regions here. So you can do this all over the globe, and the red regions are just colored where we find that there are warming trends which are inconsistent with the natural, with just climate model runs which just have natural effects and don't have anthropogenic effects, and that they're also consistent with models which have anthropogenic effects included. Now the dark red here is where the warming is actually so large that it exceeds, it's significantly above what the models are saying should be happening. So, but we see this generally over a wide range, even in the tropics, of a detectable anthropogenic signal. Now, if we look, I'm sorry, I didn't explain. This is the observed trend map in observations, and then this is the since 1901, so 1901 to 2010, the observed trend map, where we have sufficient observations. And then this is the map from the CMIP-5 climate model, all-forcing model run. So you see there's quite a bit of similarity between what has actually happened. Is that 5 minutes? Okay. And what models are saying is happening. Okay? So now, for tropical cyclones, I just want to make a point about the lack of detectability of changes in tropical cyclones. So these are various time series relevant to Atlantic tropical cyclone activity: global mean temperature, tropical Atlantic sea surface temperature, the raw hurricane counts in the Atlantic basin since the late 1800s, and then this is US landfalling hurricanes. So you see there's a global warming trend here that we're all familiar with, and also a warming trend in tropical Atlantic sea surface temperatures. There appears to be an increasing trend in hurricanes in the Atlantic basin, but there's no trend in US landfalling hurricanes. So there seems to be a conundrum here where we have this warming of the tropical Atlantic, and there appears to be an increase in hurricanes, but no increase in US landfalling hurricanes. So what we've done is to make an adjustment to the full time series where we include the fact that we had limited ship track density in the earlier parts of the records. So we conclude that it is likely that some storms actually occurred which were never detected because they never made landfall in the earlier parts of the record. If you make that adjustment, to then this full hurricane count, then you no longer have a rising trend in hurricanes. It looks a lot more like U.S. landfalling. This is not proof that there's no trend in basin-wide hurricane activity, but there's a clear suggestion from this analysis that that's the case. So this is one of the reasons why we're unable to conclude at this time that there's a significant rising, long-term rising trend in tropical cyclone activity, looking in the Atlantic where we have the best long-term records. Now, we try to use models to look at this issue as well, looking into the future. So we run climate models for a number of years and try to find the hurricanes that actually happen in these climate models and even downscale them into higher resolution models so we can look at intense hurricanes. And so this is our future projection from these climate models, just of category 4 and 5 tropical cyclones around the globe. This is our simulation for the present day, and this is our simulation for the late 21st century, and you see there are areas where we're getting, especially near Hawaii and places like that, where we're getting more of the category 4 and 5 hurricanes in a warmer climate in our model simulations. Now keep in mind we've not been able to detect this trend yet in the observations. This map is just showing in yellow where our models are projecting increase in category 4 and 5 hurricanes activity. They're called typhoons in the West Pacific and so forth. Green is where the models are projecting a decrease, so we're not projecting increase everywhere, but over most of the globe. So again, keep in mind a model projection, so we cannot be as confident in that as we are, say, for temperature. This is just in the Atlantic basin. The percent change in category 4 and 5, an increase with some scatter depending on which climate model we're downscaling in this exercise. But we're also showing a decrease in the weaker storms, the category 2 and 3 hurricanes or the tropical storms in category 1. So that's something coming from our climate model peaks into the future. The models are suggesting fewer storms overall, but more of the most intense tropical cyclones. Okay, so I won't go into this. This is just a look at El Nino and what the future, whether we can detect anthropogenic changes in El Nino, but this has already been covered somewhat by the previous speakers. So I'll just skip there. Just my point is that, as mentioned previously, there's a lot of multi-decadal fluctuation in El Nino variability, so it's really difficult to see any trend arising in changes in ENSO, whether we look at the historical record or these long paleo records. The last thing I want to talk about is heat stress changes. And again, these are model projections. We are seeing detectable anthropogenic changes in temperature in the tropics. But now these are model projections of how climate change is expected to change a temperature-related variable, a heat stress variable, which includes both temperature and moisture effects. It's called the wet bulb globe temperature. So at the top here we see a sort of the 1971 to 1980 distribution of wet bulb globe temperature. And this scale here, I'm sorry if you can't make this out, but the blue areas are where the heat stress it begins to affect human activities. So you begin to start to have to reduce your activities from the full level once you get into sort of the blue. So we see that, and this is referring to unusually warm months in the sort of pre-2000 conditions. So there were some regions of the globe, especially say in India, places like that, where some regions of the tropics where we already have a case where heat stress can reduce human activity. Now, we already see this blue region expanding here for the present day because there's already been some global warming. That's increasing the area. Now we're starting to get into some regions where heat stress is causing, say, a 50% reduction in ability to do heavy work here, indicated by some of this green and yellow regions. But now if we take this forward and we continue to have pronounced warming as indicated by the climate model, so if we go forward a century to the end of the 21st century, now we have this huge expansion of area covered by this region where heat stress is basically inhibiting our ability of humans to actually work outside. So this is that's why I mentioned it's sort of like the tropics. The tropics is expanding to where we are. Oops, excuse me. the tropics is expanding to where we are here. And then if you keep going to the end of the 22nd century, eventually you get a large parts of the tropics, even extending into our region of red areas where basically it's virtually impossible to do outdoor work during these types of hot periods. And this little scale here, which I'm sorry you can't read, but I'll summarize, is basically if we continue, if these climate model projections are credible and we continue to warm the climate system, the conditions which we're seeing in places like Calcutta and Bahrain today, those conditions could reach into even our region, even New York City could have heat stress conditions similar to what we see today in Calcutta and Bahrain. So that's what I mean by models are suggesting that the tropics may be coming to us. So I'll just stop with that. This is just a repeat of what my key messages were, and I'll be happy to talk about this more in the panel session. Thanks.
Thanks, Tom. Now I'd like to ask Laura to come up.
Okay, hi everybody. So I think I'm going to change gears a little bit from the previous two talks, and I'm not a climatologist, so the kinds of things that I'm interested in, I'm a biogeographer, and what I've been working in the last 15 years is in sort of trying to understand how landscapes change in tropical regions, specifically in rural areas of Latin America and in the tropics. So what I want to do today is sort of talk a little bit about sort of these disturbances that Tom mentioned, hurricanes or droughts or fires, and how that affects specifically tropical forests. One of the things that I'm very interested in when you think about tropical forests in rural areas is that these are used landscapes, no? And so they are not primary undisturbed forests, but they are actually a lot of regrowth and a lot of secondary forests present. So I want to talk a little bit about sort of resilience, forest resilience. So it's a bit different, again, from the previous talks. So to frame my talk today, I wanted to sort of bring this to you because it was an interesting debate, at least in our across my research community, about the effect of trees on climate. And when I read that, the New York Times OPD, to save the planet, don't plant trees, you can imagine every kind of person working on forest, that it was a little too much to see it. But basically, it was an atmospheric scientist trying to understand atmospheric chemistry and just looking at the effects of volatile compounds in the atmosphere and how these actually will not cool the planet, but actually might warm the planet more. But what this sort of illustrates, this OPD and sort of the responses, is how sometimes we can think about forests in a very general way, and maybe some of the things that she's mentioning, at least in terms of the effects of these compounds, might be more appropriate for boreal forest. They don't necessarily apply to the tropics, and when we think about obviously tropical forests, we always think about the effect of cooling that they have, especially in terms of carbon sequestration and the developing of clouds and cooling through cloud production. So there was a lot of sort of conversations around that and around this debate, and specifically one of the groups that I work with, this partners group that I don't know if you can see it here, but it's basically trying to understand reforestation and regrowth in the tropics. Was sort of like, okay, how can we make the similar claim, but sort of the opposite, and just bring back the importance of forests. I mean, in not only in terms of climate, but biodiversity and obviously people's livelihoods. So this is oh wow, that really washed out. So this is actually a map that I wanted to show in terms of the importance of tropical forests on carbon sinks. So obviously deforestation is second to fossil fuels in terms of CO2 emissions, but when we think about carbon sinks, the tropics are really important. And what this map shows here, to know which is the... is that, okay, so this is our sort of carbon emissions through the deforestation, and these are carbon sinks. So we see that regrowth actually is a very important piece of that carbon pools in the tropics. So it's very important for us to understand how this happens. And there's a lot of uncertainty, really, in terms of how much secondary growth exists, what are the patterns of those landscapes, and so I think that's going to be sort of a critical aspect to understand. So my work is trying to look at disturbances and how that affect dry forest, and specifically in the southern Yucatan. I've been working in this region for around 15 years, and basically what it is that there's a lot of things going on in this region. So it's not only hurricanes, or that are actually quite common. There are droughts that, I think Laila mentioned some during the Maya period. But it's also a place that, people actually cultivate and use those landscapes. So they do, agriculture, they have agroforestry. So it's very important for us to understand how these kinds of disturbances actually relate to the quality of the forest, the kind of forest that we have, the patterns of forest that exist, the rates of deforestation and regrowth that exist. And I think those are things that should be important when we think about also climate in the tropics. And an important thing in my own research as a geographer is trying to separate the effect that these disturbances like hurricanes and droughts and fires have from what people actually do, especially when we think about programs like RED, and maybe some of you are familiar with those, but the idea is, okay, how people are really affecting forests vis-a-vis how really, what are the kinds of disturbances that forests are sort of used to and how they sort of react. So I'm going to just tell you a little bit about some of the work that we've been doing. So we're looking at basically the effect of land use on damage after Hurricane Dean. It's a hurricane category 5 that occurred in the peninsula in 2007. And just looking at different kinds of land use and forest age and levels of fragmentation, just trying to understand what was the effect of the wind disturbance. And so what we found is basically that secondary forests tend to do much better job in resisting the hurricanes that primary forests. So what this said is, like, if we were to link this sort of results to some of the things, for example, that Tom talks about, when we see maybe in this region an increase in the number of hurricanes that are going to occur, not number of hurricanes, sorry, the strength of the storms are going to be category 4 and 5, so the wind disturbance is going to be quite high, even if the storms are not that frequent. What it means to these forests that have been already used is that you are going to sort of push towards having more of a secondary forest, and that secondary forest is going to be more sort of dominant than necessarily allow for the time to have this sort of old growth there. And that's not only reflecting in terms of structure, but it's also reflecting in terms of the species that are present. So species that are more dominant in these that resist better these disturbances are usually those of secondary species. So let me tell you a little bit about the methods that we use. So basically what we're trying to do is trying to understand the effect of these storms on the landscape, sort of what we consider a regional level, using remotely sensed data, MODIS, and trying to look at sort of the variability in EVI, which is basically some sort of vegetation vigor, and see if we can use those variations in order to sort of map the damage at the regional level that the hurricane has, the wind has on forests. And I don't know. Actually, I'm going to show you the map in a minute. And so the idea is to start understanding regionally how the patterns of damage are, and then link these to plot work data. So we develop a plot work across this Mesoamerican biological corridor, and we are trying to just look at every single tree and measure damage in terms of structural damage and look at species at the plot level, and then try to monitor how these areas actually recover from the wind damage. So what is important here is that if you notice, and I need to find, is that okay, so this is these two biosphere reserves. This is the corridor that we're working with. This is the path of the hurricane that we're studying. This is in 2007. And these areas are ejidos, which are like areas where people work. I mean, it's community-owned land. They do agriculture. And so what we're looking in these plots are distributed across this region, is that there are plots within, there are not forests that are isolated from use. These are forests that are used by different communities. So we're trying to understand not only the effect that wind has on the forest itself, but also how land use has an effect on that as well. Okay? So this is the map that we developed using MODIS data, just showing us sort of the EVI variability. And obviously, even if it's a hurricane, 5, 4, 3 here, what we see is that the pattern is not necessarily very homogeneous. So if you were to have a category 5 wind disturbance, we will have basically all the leaves gone, and you expect that you will have basically here a lot of the same color. But what you see is there's a lot of variability in terms of pattern, and that relates with the different kinds of forest types that exist and levels of fragmentation that are related to land use. And so what we're trying to do is sort of to relate these patterns with this, and what we actually found is that selva mediana and actually secondary selva mediana tends to be more affected by the wind disturbance than, for example, bajos or other kinds of forest. Another result that we have, this is from the plot. So I have 5 minutes left? Okay, thank you. So another result of measuring the damage of this forest, again, I don't know if maybe I'm repeating myself, but what we think that is important for us to understand is that sometimes a lot of the work when you're looking at disturbance on forests, and tropical forests, is that you tend to remove other kinds of disturbance from them. So you tend to obviously just look at older forests. So what we are trying to do here is just trying to look at, again, these different kinds of land use. So this figure here that I'm trying to show is looking at how different levels of damage done by wind disturbance are related to the structure of the forest, the number of stems and basal area. And basically what I want to show with this is that if you were to have the distribution of your points, so each point of this is the damage by plot. So these are the 90 plots that we measure. And so we are looking at no damage. This is small branches, medium branches, snaps, tree uprooted, bends, and deads. And so what you expect if you look at all the plots and the distribution of the proportion of the stems and the basal area, if they are all across sort of 1, is that the damage is sort of homogeneous in terms of structure. All trees of all sizes more or less got the same kind of damage at that level. So if you have below 1, what you show is that basically bigger, you have more stems with a small basal area that were affected, and then you will have, in this case, bigger, you will have a lot of more stems affected that are sort of bigger. The idea is where smaller trees or bigger trees affected the most. Smaller trees tend to be secondary growth, bigger trees tend to be primary forest. And what we found is basically bigger trees tend to obviously be more affected by these kinds of disturbance, not the smaller ones. And so this is what we're trying to show with this. And when we're looking at the recovery, what we see is that actually in less than 5 years, and it's basically this graph here that I want to point out, is that this is the number of stems that were 5 centimeters or more deviation within those plots before the event. We see that in 4 years we're getting, in terms of stems, more or less to the same level, and the same goes with basal area. So these forests tend to recover relatively quickly, but again, they're dominated by this sort of secondary type. So what is interesting to us is just how can we link these kinds of disturbances to other things that are actually occurring in that region. So when we think about land use, we need to link these to hurricanes, fires that occur, because these are areas where people do shifting cultivation. Fire is an important tool for them to do agriculture. So how, after a hurricane, when you have this biomass available to you, how that's going to increase or actually increase the number of wildfires that were not even present before. And so basically what we want to do is to be able to connect these pieces together. So just to conclude, for us, in order to put basically land change and landscape change and deforestation as part of this system and the climate system that we are discussing today, it's sort of important to understand sort of what kinds of patterns of use exist. How people are doing, most of these forests are really used. They are not, isolated or, removed from human activities. But so how these kinds of activities, subsistence farming or some sort of more market-oriented practices are going to be really affecting, forest fragmentation, and really these, added to the environmental disturbances that are present there can sort of, enhance some of the effect that these disturbances have, and probably have effects on fragmentation and changes in forest. So to go back to the safe, don't plant trees to save the planet. So I will say that maybe obviously we need to think more than just atmospheric chemistry, but we need to be thinking about how these places are so important for biodiversity, for livelihoods, and also for the way that this disturbance locally really interact with this forest. So these are some of the people that I work with, and that's it, I think. I think I did 15 minutes.
So I'd like to thank all of our panelists, if we can right now, for the nice overview talks. So in the interest of kind of keeping things rolling, rather than asking my question about key uncertainties and what I should study in the next 5 or 10 years, maybe I'll turn it over and see if anyone in the audience has any specific questions about any of the things our panelists have shared with us. In particular, any students, and I'm looking at some of the students out there. No questions? Okay, so maybe you can then answer the question that I have, which is, from your own perspective in terms of the work that you do, and you kind of perhaps have alluded to these, but what do you see, or what would be sort of the key uncertainty? What's the key question that you would like to solve in the next 5 or 10 years concerning your science and its relevance to the tropics? Maybe that's asking a bit much for 5 minutes, but anyone have any thoughts? Tom?
Yes, I think that, is this on? Yeah. First of all, a lot of the impacts that I discussed scale with global mean temperature. For example, the heat stress impact. So we would like to better pin down what the actual climate sensitivity is, the transient climate sensitivity of the planet, because there is still a considerable amount of uncertainty in this, whether one talks about equilibrium climate sensitivity or transient For example, IPCC, I think, has a range of 2 degrees to 4.5 degrees, or 1.5 degrees to 4.5 degrees for equilibrium climate sensitivity. So that implies whenever I'm showing some kind of projection, there's going to be this overriding uncertainty. And also we find that in addition to that when we're looking at things like changes in Atlantic hurricanes, those in our models, those seem to depend on how the Atlantic warms compared to the rest of the tropics. So not only do we need to know how overall temperatures will change, but we also need to know second order types of effects, like how the distribution of temperatures will change in order to make more confident statements about things like Atlantic hurricanes. So that's a tall order. Mm-hmm. It's a tall order for the climate change community. I think that'll keep us busy as we're struggling with things like the global warming hiatus and so forth. But going forward, to better pin down overall climate sensitivity as well as some of its regional structure, which can affect these impacts like hurricanes.
Anyone else have a comment or thought? Laia?
So, in my personal case, I think that I'm going to try to invest a lot of efforts trying to get more tree-ring records from the tropical Andes, specifically, because I think that it's a region with a lot of potential, that there is some kind of seasonality due to the high altitude, and also due to the migration of the ITCZ. And I think that the lack of records there, it's because no one have invested the efforts going there and taking the right samples. So you can do a quick trip to Alaska and you get the best samples ever and you will not have any issue, but in the tropics it's more complicated and maybe you need like more than one trip to find the right species, the right places, but it's not impossible. And I think that with the experience of NADA and MADA in Asia and all the information that this drought atlas can give on spatial resolution and temporal resolution, it's really worth to invest efforts in other regions like South America in my case, but in Africa there's a lot to do as well.
Laura?
I mean, obviously, I think that, one of the things that we really don't know, and obviously it's not at the same time scale that you guys are talking about, but it's just understanding land change. It's just very, very challenging, and in the tropics it's even much more difficult. And even with tools like, with remote sense data and at different kinds of resolutions, it just gets to be extremely challenging to get sort of accurate representations, not only of the amount of change, but where that change is actually occurring. And when you add into this the sort of understanding regrowth and tropical regrowth, which is something that happens at different time scales, and just trying to understand the structure and composition of that regrowth is being quite difficult. And especially to expand into regions and not making it just very local, because I can spend a lot of time in those plots and telling you everything about those plots, but how can I extrapolate that and then just talk about and make it into maps like those maps that they can use? Right. That's extremely, extremely, extremely challenging. So you can see that disconnection. And I think that's part of this conversation of saving trees and,
sure.
And saving the planet and planting trees. So.
Yeah. Mark?
Well, I guess I'm actually most interested in trying to understand the causes of the aridification of Africa several million years ago. In order to do that, it'll be necessary to try to understand the climate now. And that does speak to why exactly, what it is that the models are not getting right and why they're not getting it right. I think some of it is the temperature patterns in the tropics, but there's something else. And the other question that interests me is the relationship between climate and conflict. We are part of a paper that came out a few years ago showing that there are actually more conflicts worldwide in an El Nino year. Mm-hmm. Now, I think that one of the things to fear about climate change is whether this will unleash the long demonstrated proclivity of people to kill each other. And I think that's a major concern. And I think one of the things that we don't understand terribly well is how the conflicts arise out of environmental stresses.
Thanks. I think, Xenia, you had a question?
Hi, Xenia Morin from Rutgers University. I'm not a climate scientist, but come from the plant community. And I know places like the World Resources Institute and others have been looking at climate and feeding the world. And it seems to me that some of the critical factors that we need are to know when it's going to be hot, because if it influences pollination, if it influences our crop production or our food animals, knowing how long and when or where is going to be really critical to how the planet responds. And so I want to kind of add that if we're talking about New Jersey becoming tropical, that endangers many of our crops that we're growing now. It endangers our pollinators. And to think maybe on different scales. I know much of your research is on a large global scale, but pinpointing how hot the summers will be or those critical times during crop production might be important. So I'd like to just add that.
No, I think that's a good point. Any response or comment?
And in my talk, I did touch on heat. I was using heat stress, which includes moisture. So maybe plants are responding more to just temperature, but the reason why I was focusing on the heat stress is because humans
Sure.
are impacted by the combination of temperature and moisture. But I think also it's important to keep in mind, I was showing relatively long-term projections, so it's not just around the corner that New Jersey will become tropical. This was a century from now or 2 centuries from now if we change the radiative forcing of the planet by adding 8.5 watts per square meter of additional forcing by basically going gung-ho on fossil fuels for the next 200 years. That's when you really I think are risking having New Jersey turn into something a bit more like the tropics. If you just gung-ho for 2 centuries, it's not just around the corner,
Right.
But I think the models are giving us kind of a picture of what kind of future we may be buying into through continued burning of fossil fuels over the long term. Not next year, but this is a problem. It's again to keep in mind that we'll continue to grow according to the models as long as we continue to burn fossil fuels.
Laura?
So I just wanted to comment on, I mean, I know that the question was most related to New Jersey and sort of agricultural practice in New Jersey, but when you look at, effects of climate, obviously that affects the places where I do work too, and these are places where people have been doing farming for long time and still do, as part of their subsistence. And so one of the things that happens is that people that uncertainty that you mentioned is so critical to them just to be able to just make it, to plan for the following year. And there is a lot of understanding that they already have, and that they would like to have more, sort of understanding of, okay, how certain are you on your prediction more than this is what it's going to be? Because then they can plan around it. So some of the things that I see with the farmers there is that they sort of, to use the word adaptation, which is going to be the panels in the afternoon, they sort of shift and change and adapt to some changes. Sometimes it's the sort of like the level of uncertainty that they have to deal with more than anything else. But you see them changing, when they start planting, when they start, what kind of crops to grow even. And so it's very interesting just to see that as an example as well.
One of the interesting things is if you look at, if you work with plants, which I don't, but of course it's very complicated and exactly when it rains and how much it rains and how long a dry spell you have and all of these things matter. On the other hand, we have all sorts of evidence that relatively crude climatic indices, like some measure of El Nino, for example, have significant correlations with crop yields. So, for example, the corn yield in the United States goes down in a La Nina year compared to other years. Now, either that is in fact, so the suggestion is that these gross measures actually contain some information, despite the fact that none of us have worked very hard to see how they translate into the very specific kinds of information that farmers would dearly like to have. The second thing is that we will never have these very date-specific kind of things with any high degree of certainty, because they relate to aspects of the climate system that are internal variability and that are intrinsically unpredictable. That is, even if we had perfect models, which we certainly don't, it would there are aspects that that say that implicit in the question that we'll never be able to do because they're unknowable. Okay. On the other hand, we can project forward ranges of uncertainty, with ranges of uncertainty rather, what sort of changes you might anticipate. That said, a lot of the work on projecting what will happen with climate change is done with crop models. And these crop models can work very well in highly regulated conditions where people know exactly the farm management practices, soil properties, and so on. This is not the case for most of the world, okay? And these crop models do not do very well in those circumstances. So one of the difficulties in projecting things forward is to even having a better way of translating, even if you knew the climate certainty, our ability at the moment to translate that into the implication for crop yield is not what we need to project this globally. So that's above my pay grade, but that's something that that definitely needs to be worked on if we're going to continue to try to make these projections. Finally, I'll say, and this goes back to the heat stress idea, that there is something that I don't completely understand, but and it's this, that there may very well be a kind of threshold, as there does seem to be for human beings, for plants. And that is to say, even if you start genetic engineering, there may very well be some kind of temperature threshold that you're simply not going to beat, And so if things warm up, as Tom is projecting, then there are an awful lot of crops that are grown in those places that, it just won't be possible to grow anymore in any form.
Any other questions?
Okay, I find it really fascinating that, hi.
Could you introduce yourself?
Yes, I'm Rezwan Razani, Footprint to Wings
Okay.
nonprofit. Okay. Yes, so I'm really interested in seeing a map of I was really pleased with the sea surface temperature map, the anomalies, and maybe a carbon sink map. Is that what you were saying when you said you wanted to extrapolate this to a map, some kind of global, so we can see where, and one of the reasons I bring this up is just that op-ed you had about forestry. A lot of my friends are vegan, and they've been saying, go watch Cowspiracy, and cows are totally destroying the climate, and it's 40% of human anthropogenic impact. So I really kind of want to have something to look at to kind of show the different impacts and what is taking in carbon and what is not.
So that map that I was showing, that didn't look really good on the screen, unfortunately, but that's an article in Science, and he's basically showing just the net amounts of carbon that are stock and forest, sort of primary forests, the ones that are happening as regrowth is occurring between 2000, 2007 and another period of time, and then how much is being emitted by deforestation. And so those bars, if you see, there is a huge difference between what it is carbon sinks in the tropics compared to boreal forests. So this issue, for example, that Nadine was making on not planting trees was mostly more appropriate to boreal forests than necessarily tropical forests in terms of so those, and I think you can go to our website and just see more of those nuances
so
there.
that kind of information, it does show also grazing and everything.
It's just what I was trying to say with the challenges in trying to know exactly where that, where that's occurring. Probably that's what makes those maps, or making those maps a little more.
Well,
more
and if I
difficult.
can interject, I know DOE is about to launch a program in the next few years, next generation ecosystem experiment for the tropics, basically to address the question of the carbon sink.
Yeah.
What will be the fate of carbon in tropical forests in the 21st century? So there's still a lot of uncertainty about that issue. Any other questions from our audience? Well, if not, I'll turn it over to Jim, who will provide probably the most important information of the day about lunch. So let's thank again our panel.